Section 5.3 today. We skipped 5.2. Today we are going to expand what we learned in 5.1 and continue to look at orthogonal projections. To do that, we will first introduce what orthogonal transformations and orthogonal matrices are, and we are also going to introduce the concept of the transpose of a matrix because it's very useful for orthogonal projection. So the definition of an orthogonal transformation T is if the transformation preserves the lengths. So here, if the length of a vector x is preserved after being transformed by T, then we call this transformation orthogonal. This, of course, has to be true for all vectors. And if we have a linear transformation T that is orthogonal, then the matrix of that transformation is also called orthogonal. So, just to foreshadow what we'll see in a minute, we use the word orthogonal for matrices and transformations. These require the basis to be orthonormal. So these two words are a little bit easy to mix up, but we'll see that if a matrix A is orthogonal, then its columns are orthonormal. So keeping in mind that the definition of an orthogonal transformation is that it preserves the length of all vectors, show that a rotation in R2 is an orthogonal transformation. Well, certainly it is, because when we rotate vectors, it's not changing their lengths. So we're done. Write the orthogonal matrix A of the transformation. Here it is. The first theorem we talk about is that orthogonal transformations also preserve all angles. So by definition, they preserve length, but as an automatic side effect, they also preserve angles. How can we think about that? We can think of triangles here. If we have vector u, so if we have vector u, vector v, and vector u plus v, this forms a triangle. And if we transform each of these three vectors, we know that they're all going to preserve their length by definition. And so automatically it has to preserve angles. If you think of this triangle, if you have three sides, you have no choice about what the angles are going to be. So orthogonal transformations do preserve angles. If you want to see an algebraic proof, you can find one on page 212 of the textbook. As a side note, it doesn't go vice versa. If you know that something preserves angles, it doesn't automatically preserve lengths. The simplest example is to think of a zoom. If you zoom on vectors, so if you scale vectors, it will preserve all angles, but it will not preserve length. We will now look at a theorem, or really two theorems in a row, but the second one is such a consequence, a direct consequence of the first one, that we will really first focus on the first bullet point here. Note that even though Eric Cheng had clearly pointed out the problem with these two words, he didn't copy properly, or maybe I didn't write it properly on the board. This should say orthonormal, like I wrote here, and this as well. So it's orthonormal, not orthogonal. Anyways, so let's try to prove the first theorem. It says if and only if, which means that these two statements, A and B, are equivalent. We can say if A, then B, and also if B, then A. And that's how we're going to prove it. We have to show that T is orthogonal if and only if T of EI is an orthonormal basis. So first, let's go from A to B. Here, we assume that T is orthogonal. What does it mean? It means that it preserves the length of vectors. Now, E1, E2, E3, En are the standard basis, so they all have norm 1, and therefore T of E1, T of E2, T of E3, T of En also have norm 1. Secondly, we saw that even though it's not in the definition, it's it's automatic that a linear transformation that is orthogonal also preserves angles. So given that our standard basis E1, E2, E3, they are all perpendicular, and given that T preserves angles, T of E1, T of E2, T of E3, and so on are all perpendicular. And that concludes the first part of the proof. Since T of E1, T of E2, etc. have norm 1, and since they're all perpendicular, they form an orthonormal basis. Secondly, we have to go backwards and show that if T of EI form an orthonormal basis, then T is orthogonal. How can we do that? We're going to assume that this is true. So we're going to assume that T of E1, E2, etc. have norm 1 and that they are perpendicular. And we want to reach a point where we show that T of x, the norm of T of x, the length of T of x, is equal to the length of x for any vector x. So let's start. We suppose that T of E1, E2, E3, etc., T of En form an orthonormal basis, and then let's look at what it entails for T of x. In fact, for simplicity, we look at the norm squared so that we avoid having square roots everywhere. What is the norm squared of T of x? X, we can expand it. It's a certain linear combination of the standard vectors. And since T is a linear transformation, we can do the usual process of taking out the constant and splitting the sum, basically. Now, here's an important step. This is where we are going to use the fact that T of EI form an orthonormal basis. T of E1 is perpendicular to T of E2, which is perpendicular to T of E3, perpendicular all the way to T of En. So, what can we do? We can use Pythagoras. It's written in tiny here. Let me zoom as much as I can. Pythagorean theorem. Our hypothesis includes that all the vectors are perpendicular. Let me zoom back. Alright, so that means I can split, just like when we do a squared plus b squared equals c squared. This becomes that part squared plus this norm squared plus the third plus all the ones until the end squared. Secondly, T of EI equals 1. The norm of T of EI equals 1. So each of these norms is actually just k1 squared, k2 squared, and so on until kn squared. So we've used the two parts of T of EI being orthonormal. We first used the fact that it's perpendicular to write the Pythagorean theorem, which is a part that maybe is missing here. And secondly, since T of EI has norm 1, the norm of this whole thing is k1 squared plus k2 squared and so on. And this, if you think about it, is the norm of x squared. So we went from T of x, the norm of T of x squared equals the norm of x squared. So now we can take the square root. Norms are always positive, and we reach the answer. The second part of the theorem is simply that a matrix A is orthogonal if all of its columns are orthonormal. It's very important to know. We will use it in a second, but it's not hard to prove just because how is A constructed? Matrix A is constructed by putting T of E1, T of E2 in its column. That's how we build matrices column by column. So it's a direct consequence of what we did above, since we know that T of E1, T of E2, T of En form an orthonormal basis. So, quick example, show that the matrix A given here is orthogonal. We need to check that each column has vectors that have norm 1 and that they are all perpendicular. So, two things to do. 1, 2. First, the norm of the column vectors is 1. We just show 1 because it's always the same. And then the dot product is equal to 0, so each column is perpendicular to the others. So A is an orthogonal matrix. Furthermore, if we have the product AB of matrices A and B that are both orthogonal, then that product is also orthogonal. We can prove it visually and then with a little a series of equal signs. Visually, if you have a vector x, if you proceed to apply matrix B, then the output is another vector, bx, and we know that its length is equal to x, because B is orthogonal. Then we apply A, and the output will be another vector, but again, we know that the length has been preserved. So A of Bx has the same length as Bx. And so altogether, A of Bx, which is ABx, has the same length as x itself. This is what it looks algebraically. A of Bx equals Bx equals x in terms of norms. Likewise, the inverse A inverse of an orthogonal matrix is orthogonal. We could also make a little visual sketch by just showing that it goes backwards. Of course, if this vector has the same length as that one, then that vector has the same length as this one. How do we prove it? It's a little bit more intricate than one would expect. We need to show that A inverse of x has the same length as x. We need to add matrix A. We know that A is orthogonal, so we know that this is going to have the same length as A times what we had. And then, since we know that A times A inverse equals I, these two cancel out, and we come out with x. All right, now we're introducing something very new, not at all difficult in itself, very much something we could do in pre-calculus, the notion of the transpose of a matrix. We do that because it comes very handy when we want to do projections. The transpose of a matrix is simply a matrix where you flip the rows and the columns. Here's an example. If you had column 1, 2, 6, negative 2, 3, 4, 6, 0, now the transpose of A, written AT, is 1, 2, 6, negative 2 becomes the first row. It used to be the first column. And 3, 4, 6, 0 becomes the second row when it used to be the second column. So if we have a square matrix, I can come back here now. If you transpose a square matrix and you get AT equals A, that actually translates as A being a symmetric matrix. And if when you take the transpose of A, you get negative A, then we call that a skew symmetric matrix. Find the basis of the subspace of all symmetric matrices of order 2 by 2. The basis has 3 elements. What's important to notice is these two have to be the same, so there's only 3 dimensions in this subspace, not 4. A note: given 2 vectors v and w, the dot product of v and w can be written as a matrix product. So this is a dot product, but if you take the transpose of vector v, then it becomes a row multiplied by, so vt is a row vector and w is a column vector, so it becomes a matrix product. And if you look at the result, it's going to be a 1 by 1 matrix whose entry is the result of the dot product. No big deal, but we're actually doing that quite a bit here from here on. So, an n by n matrix A is orthogonal if and only if AT times A equals I. That's quite a strong, powerful way, especially if you have a matrix, to check whether a matrix A is orthogonal, rather than checking that every single column has norm 1 and checking that every single column is perpendicular to every single other column. You may just multiply AT by A and see whether you get the identity matrix. How does that work? Well, if A is made of column vectors v1, v2, vn. So think of these as column vectors, v1, v2, vn. Then the transpose of A is AT, where now we have row vectors v1, v2, vn. If we proceed to multiply AT with A, we get this, and if you think a little bit, you will realize that is the final matrix that we obtain. So it's a large sequence of dot products, v1.v1, v1.v2, v1.v3, all the way to v1.vn, etc. So from here to there, we have to meditate a little bit, but if we know that A is orthogonal, we know that all vi have norm 1 and that they are all perpendicular. So the result is that v1.v1, which is the norm of v1 squared, it's going to be 1, and that's going to be true for every entry in the diagonal. And then v1.v2, v1.v3, etc., etc., it will always yield zeros because all these vectors are perpendicular. So again, if you have the same index v1, v1, v2.v2, v3.v3, the dot product will be 1. If you have a different index, it means the vectors are perpendicular and the dot product will be 0. To go backward from here to there, you need to think a little bit about it, but the idea is very much the same. You just think backwards. So that means anytime, it's not just for orthogonal matrices, but AT times A is a table displaying the dot products of VI with VJ. That's just a general comment, I guess, on multiplying AT with A. Here's a summary of all we've seen today. The definition of A orthogonal is that it preserves lengths. We also saw that the columns of A form an orthonormal basis if A is orthogonal. We just talked about that, and this is a consequence of the previous one. A few additional properties of the transpose that we do not approve is that the transpose of A times B is B transpose A transpose. Notice that it flips the order of A and B. If A is invertible, then AT is invertible too. At least for 2 by 2 matrices, you can think of the determinant AD minus BC doesn't change. So if AD minus BC is not 0 for A, it's not going to be 0 for the transpose either. One more, not too obvious but useful transpose property, and finally something about the rank. So we are now reaching the last theorem of this section, which we will not prove, but we will apply it a lot. So it's one of the keys of this section here. Consider a subspace V of Rn, and you know that V is the span of U1, U2, Um. So M is smaller than N typically, but it might be equal, in which case the projection would be the vector itself. The matrix of the orthogonal projection is QQT. So this might bring us back to section 5.1 because we already talked about orthogonal projections. What's different here in this section 5.3 is that now, instead of having to fiddle with numbers ourselves and use dot products like we did in 5.1, we will be able to create a matrix, which is a machine that will do the orthogonal projection for us. So we will just feed that machine any vector we want or any number of vectors, and it will just always output the orthogonal projection. So quite powerful, and this is the difference between 5.1 and 5.3, this new ability that we have to find what the matrix of the orthogonal projection is, whatever the subspace is. Again, just like it was crucial in 5.1, you have to have an orthonormal basis to be able to do that. If you don't have an orthonormal basis, and you still want to find the matrix of the orthogonal projection, you will have to wait until section 5.4. There's 3 sections in this chapter, and each section kind of is a new layer in this project of finding the orthogonal projection. So in 5.1 it was with dot products. In 5.3 now it's with an orthonormal basis and finding the matrix. And then in 5.4 it will be with any basis. It won't even need to be an orthonormal basis. So obviously it's going to be the most powerful method, but also the more complicated one. A note here, when you use the method from 5.3, you will get the projection in terms of the original basis, not a basis of the subspace. So you won't find something like 3u1 plus 5u2 and so on. I would like to just go back to 5.1 to show the difference. Here, in this exercise, we will talk about it again in a minute as we compare these two methods. We were able to find the projection in terms of u1 and u2. And then we also found it in terms of the original basis. So in section 5.3, we are only able to do part B, basically. Okay, so let's have a look at this example here. Find the matrix of the orthogonal projection onto the subspace V of R4 defined as the span of these two vectors. They look quite similar to the example in 5.1. We will go back and forth using the calculator just to show that these two methods yield the same results. There's no easy way to make sketches since we are in 4 dimensions, but you can think of V as a plane that cuts through 4 dimensions, and you want to project a 4-dimensional vector onto that plane. First step, you absolutely have to check that the two vectors that you have for your basis of V form an orthonormal basis. So do they have norm 1? Yes, they do. Are they perpendicular? Yes, they are. After that, you can just use what we found earlier, that it's Q times QT. So I will use the calculator for that and also go back and forth a little bit between the two examples, this one and the one from 5.1. Okay, so if we do Q times QT, we will find the matrix that you can see on the right. I'll just insert that matrix. Create 7, 1, 1. It's a 4x4 matrix. Now when you enter matrices row by row, it might mean that you're thinking of it as like linear equations maybe. If you enter them column by column, it may mean that you're thinking of the entries as vectors. Either one is fine. So here we want to see the projection of that vector, which I can't remember, but I'll just check. It's 1, 0, 3, negative 1. And indeed, we get 0, 1.5, 1.5, 0, just like in Eric Chen's notes. So if we go back to section 5.1, can we do the same with this example? Could we use Q times QT with this example? Well, yes, of course we can, and let's do it. So Q will be made of the two vectors u1, u2, and instead of calculating Q times QT by hand, we will just insert Q. And you know that on your calculator you can also use Control-C, Control-V. So if you select and then you press Control-C, Control-V, it works. And then menu 7.2 gives the transpose. So this is Q times QT. there's a little t. Perfect, so again I'll copy that, Control-C, Control-V, and I will multiply that by the vector that was given in 5.1, right there. And hopefully we get the same result as we did. Yes, we do. So thank you very much for listening. Have a good day.